Okay, welcome to lecture 2 of electronics 2. I actually started this recording around like 10 minutes ago, but midway through the recording, my Apple Pencil decided not to work anymore. I don't understand why. Like I was doing this, but my laser wasn't showing up. So I'm just gonna have to re-record this anyways. Okay, so like I said before in the previous lecture, electronics 1 is like a maze and electronics 2 is like a puzzle. That doesn't mean you should forget everything you learned in electronics 1. Having very, very strong abilities of doing AC analysis is gonna help you have a sense of how to determine subcomponents of your circuit when putting it all together in a more complicated circuit. So you should definitely brush up on your AC analysis. If you feel rusty, I recommend go watch my videos on BJT AC analysis, MOSFET AC analysis in the Electronics 1 playlist. Watch it, do the question, make sure you refresh yourself, and then you come back here because having a strong foundation in AC analysis is going to help you look at a big circuit with multiple transistors and then analyze is going to help you intuit the function of each of them without doing any analysis. And that's going to help you with your more complex circuits as soon as you add more transistors. So today we're going to learn how to find the gain again. All right, because just in life, like in life in general, gains are important in the gym and gains are important in electronics as well. So we got to lock in. Okay, so that being said, we got this circuit going on here. And then you can see that we have four transistors. But now you're not going to go ahead and replace all of them transistors with AC small signal model hybrid pi and then try to find V out over the in. You're not Einstein. I'm not Einstein. Even if he did it, he would make a mistake. So lock in and then use the electronics 2 method that I'm about to teach you. And the electronics 2 method is this equation right here, AV. The gain is minus GM or out. What is GM? GM is the transconductance of your entire circuit as a whole. Or out is your output resistance of the circuit. So this GM right here is your transconductance of the entire circuit. How am I saying it this way? Transconductance. This is how you say it. Okay. And R out is your output resistance. So R out is pretty easy. It's just what we did in the first lecture I posted for this course, for this playlist. But today we're going to learn how to calculate GM as well. So R out, technically, you're just going to go at the output and then find the output resistance of your circuit here. Pretty simple. So how do you find GM? To find GM, you need to disable all the DC sources, not AC, just the DC. So you can see here those filled up dots, these are all DC, and the hollow right here, that's your AC. So this you're gonna leave it alone. VCC is DC, all these are DC, so you're just gonna pop, 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 ground all of them. And what is the equation for GM itself? So this is the equation. GM is the output current over the input voltage when the output voltage is zero. It's pretty simple. You go to the output voltage, grounded. Output voltage is zero. Now, what is the output current? It's the output current right here going from ground into the circuit. And you want to find this value over the input value. Now, that being said, before I go into any analysis, I'll give you a bro code. This GM is going to be equal to the GM of the transistor that's associated with the input. So if you look at this circuit, all you need to do is go find a transistor associated with the input. Here you have the input voltage. This is Q1. Inside of Q1, there's GM1. So big GM is going to be equal to GM1. And that's going to be probably true for 99% of all the circuits in this course. So if you forgot how to calculate GM, maybe your analysis is too complicated, you can't figure it out, you're in an exam, you're in the midterm, you don't know how to do it, use this code, use this trick. So for example, if here, let's say I had a DC voltage, I had V in here at VB2, the GM would be equal to GM3. Trust me, I don't know why it works this way. It works this way though. It's not theory, it's not proved. I can't prove it. I just did so many examples that this ended up being the case most of the time. And you better trust me. And if you don't trust me that I prove it, then you're gonna have to trust me. Either way, let's find it out. So these DC voltages are grounded, and then as you can see, this is grounded on this end, and then this is going to be grounded here, which I drew right here. So that means that all of this is going to be short circuited because technically it's just this here. This point is grounded, and then this point is grounded too. So all of this gets eliminated, and in the end, your circuit gets simplified to this. And when you look at this, you still have two transistors. Again, don't go into that stupid mindset of replacing these two transistors with a hybrid pi model. You're not going to make it out alive. Okay? So you got to be smart. Again, we use methods in the previous lecture, right? You got to apply them. You got to look at the transistor and then replace them. Okay? Now, this is an AC source. It means that you can't ground the AC, right? Because we're finding GM. That means you're not going to be able to replace this one. However, you can replace the one on the above. Why? Because you have two terminals that are grounded, and you can use your cheat sheet to your advantage. So over here, I want to look at the emitter of the Q2, and I want to replace this Q2. But remember, I'm going to call this RQ2, and I'm looking at it at the emitter. So all I need to do is go to my cheat sheet, look at the emitter while the base and the collector is grounded. That's all I need to do. So I need to find such a circuit. So I'm going to go to my cheat sheet here. Okay, here I'm looking at the emitter. The base is grounded and the collector is grounded. Now you have two equations you can use for the equivalent resistance. You can use this one, you can use this one. I'm very lazy, so I'll use the approximation, and I don't want to have to write a lot because I'll make mistakes. I'll make an RO become an R pi and stuff like that. Okay, so I use this 1 over GM. So this is going to be my equivalent resistor for this Q2. And RQ2 will be 1 over GM2. Now make sure when you guys are doing these analysis, don't just write GM, please. It's Q2, so it's going to be GM2, because it's not necessarily true that all of your transistors have the exact same beta, the exact same V pi, the exact same GM. All right, they might be different, so you want to differentiate them unless the question says otherwise and all your transistors are equivalent. Okay, but in that case, then GM equals GM. All right, but here GM is equal to GM2. So that means I can replace this. Oops, where's my laser? I can replace this with a resistor. So this is what I have here. Okay, there we go. So now we have such a circuit, and unfortunately, Vin cannot be disabled when finding GM because it is an AC signal. You can't disable Vin. However, we can still use electronics 1 method. Now, you took an electronics 2 problem, you used some methods we learned in the past lecture, and then you simplified your circuit to one transistor and one resistor. Now that shouts electronics 1. It shouts some bad memories and some tears and a lot of coffee. So what you want to do, you want to bring those back, but you're a stronger person now, so you should be chill with those AC analysis. So you're going to replace this Q1 with a hybrid pi small signal model, and then you're going to find out what I out over V in is. Now, quick tip here is when you're doing this, you're giving I out into the circuit, right? You're grounding the output and giving I out into the circuit. Make sure it goes into the circuit. Otherwise, it's going to mess up with a negative sign over here, right? You always, by definition, go from the output inside to the circuit, okay? So then your minus there is going to make the formula work as a whole, and you're not ignoring your 180-degree phase shift that happens with a negative sign, okay? So keep that in mind. So what I'll do here is I'll replace Q1 with a small signal equivalent model. So this is my base. This is R pi 1. This is V pi 1. This is the voltage dependent current source, and then this is RO1. This is just hybrid pi model. Now the base here is connected to my input voltage. The emitter here is connected to ground. The output is connected to ground here, okay? And the collector is connected to GM1 over GM1. So when you look at the circuit going on here, you can already see that, hey, my emitter is grounded, which would mean that this input voltage is equal to V pi 1, all right? V pi 1 is equal to V in. Why? Because the emitter is grounded. So that's what I have in a box right here. Okay. Now, when I look over here, I see a resistor connected to ground over here, boop, 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 connected to ground, and another one connected to ground here. When I look at this, I remember right away that this is a current divider. Two resistors in parallel is going to shout at me in my head, current divider. Two resistors in series is going to shout voltage divider. So you have to be pretty comfortable with those concepts. If you're not comfortable with your circuit theory, go watch my Cookies and Cream and you'll get confident from that. Okay. So now you can see that current divider is defined, in circuit theory as such. You have a current coming in and it splits into two. So that's what I'll do. I'll give an I total and I want to find I1 and I2. Okay, so that's what I'll do. Now I total here is equal to minus the value given by this current source. So that's what I have going on here. I total is minus GM1 V in. Now why V pi? What happened to V pi? V pi is equal to V in. Okay. Now current divider equation is, if I want to find this current right here, is going to be this resistor over the sum of the two of them. All right. So RO1 over RO1 plus 1 over GM1 times the total current going in. And if you replace, one sec. What am I doing? Hold on. Oh yeah. I see. Well, I was confusing in my head I total and I out. Yeah, so this equation makes sense right here. I2, this current, is going to be this resistor over the sum of both of them times the total current. Now, what is I2? I2 is right here. However, this is my output voltage. If you look over here, this is the output. And this output is equal to I out, right? The output current going into the circuit is equal to I out. However, I define I2 going this way, and I out is actually going the opposite way. So I2 is equal to minus I out. So what I need to do is replace I2 by minus I out, and then I can isolate for I out, and I have this equation going on here, okay? And I total is equal to minus GMV in. So I replace I2 by minus I out right here, and I replace I total by minus GMV in right here. These negative cancel, and then I can write I total, I out is the current divider equation right here. Okay, so this is what it simplifies to. Now I have I out and I have V in. If I divide I out by V in, I get GM. And GM in this case is this thing. All right. Now you might say, hey Ayush, you said that GM is going to be equal to GM1, but it's clearly not the case here. Hold on a minute. Approximations. All right. That's why I love approximations. GMRO is much greater than 1. You can use this approximation whenever you like in this course. So if I divide both sides by GM, I get that RO is much bigger than GM. So if you look at this equation, this RO is going to be much bigger than 1 over GM. So this you can ignore. And RO1 over RO1 is 1, and that leaves me with GM1. GM equals GM1. The bro code works, and you all better have to trust me now, okay? So when you're in an exam and you're deep in the waters, you don't know what to do, you've been told to drive, and you don't know how to do that, trust me. Next up. So we found GM. That's half of our work done here because our equation says we need GM and we need R out. GM is Gucci. Now we need to find R out. How do we find R out? Watch lecture 1. Actually, I'm joking. I'll do it right now. It's good review. So with R out, I love finding R out. Why? Because it's Thevenin, all right? It's a Thevenin equivalent impedance. And Thevenin doesn't matter whether you're AC voltage source, DC voltage source, you're going to disable all of it. So what that means is that this V in right here is going to be grounded too. So you're going to ground everything. So this is ground, 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 ground. Okay. Now when you look at this here, this is what I'm trying to find. R out. Now when I look at this, I see symmetry. I see something going on here, and I see something going on here. Okay. However, I got to go further than that. I can't start here because I have 2 transistors. And in my cheat sheet, I don't have an equivalent impedance for 2 transistors. I have it for 1. Okay. So what that means is I have got to go further. I need to start with Q4. I need to start with the edges and then work my way in. Okay. If that makes sense. I can't replace both of these at once, but I surely can replace only this one. I can't replace both of these at once, but I surely can replace this one. So I'll find RQ4. What am I doing? Here we're looking at the collector and the base and emitter is grounded. So let's look at the situation going on there. We're looking at, what the hell? Okay, we're looking at the collector and then the base and the emitter is grounded. However, in this case, you see that the emitter is not grounded here. It's connected to RE, but that's just a general case of our case. This RE in our case is 0. So whenever you see RE in this equation, you can set it to 0, and this is equal to RO. So if you go down, I can use the equation above, set R equal to 0, and I'm going to be left with RO4. Similarly, look at this situation. You're looking at the collector, and the base and emitter is grounded. The only thing is this is an NPN. The other one was a PNP. So let's look at that. So collector, and base and emitter is grounded. RE goes to 0 for emitter grounded. So we're left with RO3. So if you go down here, RO1 actually, because this is Q1. So RQ1 is going to be equal to RO1. So you see what I'm doing here? I'm replacing this one with a resistor. I'm replacing this one with a resistor. And then I have this situation I can deal with, this situation I can deal with. I'm simplifying the problem step by step. Puzzles, right? You see something, change it. Oh, it's a smaller piece that fits into another puzzle. Fix it. Boop, 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 boop. You're going down. You have a hard problem. You bring it down nice and slow. So now I'll replace this one. I'll replace this one. So this is my circuit. Okay. Now, if you look over here, this is all PNP transistors. This is all NPN transistors. So I'm just going to call this ROP for PNP and then RON for NPN. So here what we got going on. We're looking at it this way. So we're looking at the, what is this? This is the collector, and the base and emitter is base is grounded. The emitter is connected to RE. So now if I go to my circuit, it's the exact same situation we have here. Okay. So I can use this equation right? It's the exact same situation we have here. However, in this case, RE is not grounded. RE is equal to the value of the previous transistor's equivalent resistance, which is RO4. So you use this equation, okay? And whenever you find RE, you're going to replace by RO4. And the rest, GM3, R by 3, RO3, R by 3 for this one. Similarly, for Q2, you're going to do the same thing, okay? If you go here, it's the exact same circuit here, right? You're looking at it at the collector, the base is grounded, and the emitter is connected to RE. What's the equation for RE? It's this thing. In our case, what is RE? RE is RO1, so you replace all of REs by RO1. So all of the REs are replaced by RO1. There we go. So then, if you look at this circuit right here and you're trying to find R out, so you're going to have a big resistor here connected to ground, a big resistor here connected to ground, and you're looking at it at this point, okay? So this is just a parallel combination, okay? You have something like this. This point is common to both of them. This is ground, and you're looking at it this way. It's ROP parallel with RON, okay? That's all it is. So it's gonna be this big, thick equation parallel with this big, thick equation here. So this is what I have going on here. I just wrote everything nice and neat, okay? Now I'm gonna use the approximation that GMRO is much greater than 1. So that means that I have GMRO is much greater than 1. GMRO much greater than 1. So that means I can ignore the 1 and I can ignore the 1. My equation simplifies to this thing, GMRO times RO times this thing. And the same thing on the other side as well. However, here I'm going to notice that RO4 parallel with R pi 3 is common in this case. So I'm going to factor it out. When I factor it out, it's going to create a plus 1 here, right? So I have GM RO3 times this thing, but this one is all alone. So when I take it out, it's going to leave a 1. But we do know that GMRO is much greater than 1. So that means I can ignore this one as well. Same deal on this case. Same deal, okay? When I take the RO parallel with R pi 2 right here, I take it as a common factor, this is going to become 1. And GMRO is much greater than 1, so I mean I can ignore this one. So what I'm left with is that R out is GMRO3 times this thing, parallel with GMRO1 times this thing. So this is my R out, okay? Now, if I want to combine all my answers together, AV is equal, my gain is equal to minus GM R out. GM we said it's equal to minus GM1, and R out is whatever this thing is. I don't even know what that means. So whatever this value is going to be here, and that's how you find gain. So you can see that's a combination of being good at electronics 1 and a good application of electronics 2 concepts. So make sure you have that very, very well figured out. If you missed anything in this video, go back, watch it. It's a very important video. Probably the most important video of this course, in my opinion, because if you look at this and you understand this well, it's going to make everything else simpler when the circuits get even more complicated and you started adding capacitors and all that stuff. Because, mind you, electronics 1 capacitors were short circuits. No, electronics 1 capacitors were short circuits. Electronics 2. Now, electronics 2 capacitors are not short circuits. Okay. Now, watch these videos again. I appreciate you watching it. And first video, we got like 78 views. Not bad, honestly, considering this is a pure ELG course and not ELG and then computer eng and all the other goons that got to take it. It's just ELG people. So I like it. It's a pretty good number. Let's try to bump those subscriber numbers by 100 end of semester. We'll see if we can get there. That's on you guys, though. So the more you share my videos, the faster we can reach this goal. And the more I see myself progressing towards a goal, the more the video is going to keep coming. It's up to you to watch them. So thank you, and see you next time.